this alloy of aluminum, it has a Young's modulus of 10 MSI, or megapounds per square inch. What I will call the length of it, the 3-inch dimension, is originally 3 inches. And then our original side, I don't know why I chose S, but for the 1.5 inch side, I'll call that S. Is a gauge length of 1.5 inches. And what I'll call the width is going to be the 2 inch. And we're told that the side that was originally 1.5, which I'm calling S, once we load it, once we squeeze it together with that 8-kip load, it's going to increase slightly to 1.500132 inches. In these type of problems where we have small changes in side length or any type of length, because they're so small, this is the one time you do want to keep a lot of extra digits with it, because if we do only keep 3 significant digits, we're going to see that the side length did not change at all. So usually only give me 3, maybe 4 significant digits. This changes in length are one time, keep a lot of digits so you actually see what that change is. Right, so we want to find the Poisson ratio, nu. And the new side length of the 2-inch side, I'll call that W prime. Externally, we have an 8-kip load. We have an internal force P. And I'll establish a coordinate system this way. So even though we could tell by inspection it was going to be 8,000 pounds, or really compression, negative 8,000 pounds, you still need to show that anytime you're using an internal force, you need to solve for that internal force. So the exception to this, when you're doing the, at least for the very contrived stress concentration ones, those are not relying on internal forces, because if you look at the picture, those are using external forces. So you don't technically need a free body diagram for those, but I would say when in doubt, you should be including a free body diagram. Again, anytime you're using internal forces, internal torsions, must have free body diagram. All right, with that out of the way, now where can we start to solve for the 2 things we need, the new side length W and the Poisson ratio? So again, we have, this is some of the information we know. We now know the internal force P. Right, we can find delta, the change in length along the L direction, because along the L direction is where we have this internal load P. So this is being caused by the applied load. So the delta we can say is PL over EA. And we're going to be able to calculate all of these values. Right, we know the internal load along that direction is the negative 8,000. And the sign will matter here. Along the, this is going to be in the X direction specifically, to make it a little bit more clear. Along the X direction, the gauge length, which is what we use for these calculations, is 3 inches. Young's modulus for our material, 10 million psi. And the cross-sectional area, again, this is going to use the original lengths, not the stretched lengths or compressed lengths. So originally, it's 1.5 inches by 2 inches. So the change in length along the X direction, 0.000, so 3 zeros, 8 inches. So we found the change in length in the X direction, or along that the 3-inch direction. How does this help us find what we need, that W prime and that nu, the Poisson ratio? Yeah. Right, we can start with the strain in the x direction, which is going to be the change in length in the x direction divided by the original length of the x direction. We just found the change in length was a negative .0008 inches, and originally it was 3 inches long. Oh, we want to double check the sign here. It's in compression. We're swishing it together. We should expect it to get smaller along the direction that we are applying this compressive load. So the delta is negative. We should also expect a negative epsilon in that direction. These are both in inches. The strain in the x direction, to 3 digits, we get a negative 267 times 10 to the negative 6 inches per inch. Our ultimate goal is we can find Poisson ratio is defined as negative. In this case, it'll be the strain in the y direction over the x direction or z direction over the x direction. The unloaded is either y or z in this case, but the loaded is what I over here designate as my x direction. So if I can find either of these strains, y or z, I'll be able to calculate Poisson ratio, which is one of the things I'm interested in. So which of these strains can I calculate according to at least the coordinate system that I have set up here? Right, so what I'm calling the y direction, right, which is the 1.5 inch direction, I can calculate because I'm told the stretched length of it or the loaded length of it, and I know the gauge length of it. So I can calculate the change in length, which is the current length minus the gauge length, the 1.500132 minus its gauge length of 1.5 over its gauge length. It's larger than it originally was. We should be getting a positive value for the strain in the y direction. In the y, we get a positive 88 times 10 to the negative 6 inches per inch. Now if we come down here, we can calculate nu. We just found strain in the y direction. Previously, we have the strain in the x direction. These negative signs cancel out, which they should, so we get a positive value for nu. The Poisson ratio here to 2 digits, 0.33. Again, a pretty normal value we get for nu for most engineering materials. Because these have the same denominator and they're equal, they have to have the same numerator. Right, so we can go right to this. We know the strain, therefore, in the z direction must also be 88 times 10 to the negative 6 inches per inch. Right, so we know the strain in the z direction. So how can we tie it all together to get the new length of what I call W, the 2-inch length? If we know now the strain in the z direction, we know that strain is defined as change in length over the original length. So for the z dimension, the new length is omega prime, which we don't know, but we know is originally 2 inches from the omega naught. So the strain is going to be the new length minus 2 over 2. 2.000176 inches.